Hi guys, it's Daniel here, and today we're going to do 2015 AMC 12A number 25. So, upon looking at this problem, one may want to not do it because it looks extremely hard, with too many circles, a bunch of weird expressions, and it just looks like a headache to do. However, after understanding the problem itself, the problem actually becomes a bit more manageable. So first we have to actually understand what exactly is going on in this problem. So the problem says we have a collection of circles tangent to the x-axis in the upper half plane, and it is constructed as follows. First we have a layer L0 with circles of radii 70 squared and 73 squared. And for k greater than or equal to 1, the circle is in the union from j equals 0 to k minus 1 of L sub j, which basically just means the circles in L0, L1, L2, all the way to L of k minus 1 are ordered according to their points of tangency with the x-axis. So, for example, when k equals 2, we have that we consider the circles L0 and L1s, and in order of their x-axes, we draw the first circle, the second circle, and the third circle. So the order is the first circle in L0, then the first circle in L1, then the second circle in L0. So now once we have this order, we draw the layer L sub k by drawing the circle tangent to the first two circles, then the circle tangent to the second and third circles, and so on like that. So basically what this first big chunk of text is saying is that we first start with two circles, both in L0. Then we draw the circle tangent to both of them in the x-axis. Then we draw the two circles tangent to them in order, like so. And then we draw the circles tangent to those, and then so on like that. So the idea for this construction isn't very hard in the first place. So now that we have the idea of the construction itself down, we have to find summation. So first we let S be the union from j equals 0 to 6 of L sub j, which is just the union of L0, L1, L2 through L6. So basically just the first 7 layers of this configuration. And let R of C be the radius of the circle C. And we want to find the sum of C in S of 1 over the square root of the radius of C. So now that we've understood the problem, it doesn't seem much easier because there's still this really weird summation. So to assist in finding the answer to this problem, we have to break the problem down into smaller chunks that are more manageable. So the first question that we want to naturally ask is, given two circles that are tangent to each other and the x-axis, can we find the radius of the third circle in terms of the first two circles? And of course we can find this in the standard way by drawing centers to centers, centers to tangency points, so on like that, and using Pythagorean theorem. However, I'd like to show a different way that also solves this problem and is a more general method. And this is by using Descartes' theorem, or Descartes' theorem. Descartes' theorem uses this configuration. We have 3 circles, and we want to find the radius of the circle tangent to all 3. There are, in fact, 2 possible circles that satisfy this, the small circle and the big circle. So, in order to use this theorem, we have to use an idea called the curvature of a circle. And basically the idea is that the curvature is the the reciprocal of the radius. However, there is a special case in which the circle is internally tangent, for example this circle, for which the curvature is in fact the negative of the reciprocal of the radius. However, in this case we won't be dealing with this, so we can just pretend that the curvature is just the reciprocal of the radius. So what does Descartes' theorem actually say? Well, it says that if we have the curvature of the 4 circles be k1, k1, k2, k3, and k4. For example, if this is circle C1 with curvature k1, curvature k2, curvature k3, and curvature k4, then they satisfy this relationship. The sum of all the k's, so k1 plus k2 plus k3 plus k4, squared is equal to 2 times the sum of all the k squared. So k1 squared plus k2 squared plus k3 squared plus k4 squared. So how do we actually use this fact to solve this problem though? We see that we have 3 circles, 1, 2, 3. However, we don't have a 4th circle that is tangent to all 3. Or do we? This line is tangent to all 3 circles, and we can kind of think of it as a circle in itself. Well, what type of circle it is? We can sort of imagine this as a circle that just continues both ways and doesn't really curve, but it completes itself at the point of infinity. So this circle is in fact a circle with infinite radius. And the reciprocal of a circle with infinite radius, well, the curvature would just be 1 over infinity, which is kind of 0. And this also makes sense by itself because a line has 0 curvature. So we can actually use this formula for this circle, this small circle, and this huge circle, which is just in fact a line. So let's see what happens when we plug these numbers in. Let's let k4 be the line, so this equals 0. And now we have k1, k2, k3 satisfy the following relation. We k1 plus k2 plus k3 is squared, which is equal to 2 times k1 squared plus k2 squared plus k3 squared. And now once we expand and simplify, we get k1 squared plus k2 squared plus k3 squared is equal to 2 times the value of k1, k2 plus k2, k3 plus k3, k1. And if you have ever expanded the Heron's formula, the stuff that's inside the square root, you'll find that the answer is very, very similar to this expression, except for the fact that instead of squares on the left-hand side, we have 4th powers, and instead of just to the power 1 on the right-hand side, we have squares. So this motivates the factorization of this into the square root of k1 plus the square root of k2 plus the square root of k3 times the square root of k1 plus the square root of k2 minus the square root of k3 times the square root of k1 minus the square root of k2 plus the square root of k3 times minus square root of k1 plus square root of k2 plus square root of k3 equals 0. So now we have several different possibilities. Clearly the first value must not be 0 because otherwise k1, k2, and k3 are all 0, which means their curvatures are all 0, which doesn't make sense. So these other terms might be 0 though. So let's first look at one term. Let's let k1 and k2 be this circle, so k1, k2, and k3 is this circle. So clearly we see that the circle with k3 curvature is smaller than the circles with k1 and k2 curvature, which means that the curvature k3 is greater than both k1 and k2. However, if this term that's bracketed is 0, then that means k1 square root of k1 or square root of k3 is equal to square root of k1 minus square root of k2, which means that square root of k1 is greater than square root of k3, which is bad because we know that k3 is greater than k1. And similarly, if we try to set this term equal to 0, then it also doesn't work because we get square root of k2 minus square root of k1. However, if we set this bracketed term to 0, then we get square root of k3 equals square root of k1 plus square root of k2, which makes sense because this means that the curvature of k3 is greater than both k1 and k2, which means that the radius of the circle with curvature k3 is smaller than that of k1 and k2, which is exactly what happens in this diagram. So this is the formula we want. And now replacing the k's by the radii of the circles, we get that if this has radii r1, r2, and r, the following formula holds. 1 over square root of r equals 1 over square root of r1 plus 1 over square root of r2. And this formula is actually very nice because look at what we're trying to sum in the first place. We're trying to sum the reciprocal of the square root of the radii of the circles. And this relation gives us a way to find the 1 over the square root of radius of one circle in terms of 1 over the square root of radius of some previous circles in previous layers. So now we can theoretically represent all these terms in all the circles C and S in terms of 1 over the square root of r of C, where C is these two circles. Now in order to make our lives easier, I'd like to define another function called big R of C, which is simply defined as 1 over the square root of little r of C. So basically this just means that now we are summing from C and S of big R of C. And now our formula here implies that big R of C equals big R of C1 plus big R of C2, where this is C1, C2, and C. So now we see that using this formula here, we can determine big R of any value, the big R of any circle in terms of big R of C1 and big R of C2, because we just recursively use this formula. In addition, we also know the values of big R of C1 and big R of C2 because the radii of these two circles are 70 squared and 73 squared. So in fact, big R of C1 is equal to 1 over 70, and big R of C2 is equal to 1 over 73. And in order to make our lives easier, let's set these to be equal to A and B. So now what we want to do is find the value of big R of C, where C is in S, in terms of A and B. In order to do that, we'll try to find a pattern. So here is a table of big R of C. Let's see, L0, L1, L2, L3, etc. So at the start, we have A and B. Then we have A and B, but also A plus B, because we used this property by summing A and B to get A plus B. Now we do the exact same thing. We bring down A plus B, and fill in the gaps with 2A plus B and A plus 2B. So these are summed as follows. And we continue in this fashion. So now the question is, what is the row of this table when we are looking at L6? So let's try to find a pattern first. We first note that the coefficient of A and the coefficient of B are the exact same thing because they're symmetric. So all we need to do is try to find the coefficient of A. So in this case, the coefficient of A is 1. Here it's 2, and here it's 5. So what sort of pattern emerges from this? Well, let's try to calculate what the coefficient of L sub k plus 1 is given L sub k. So if the coefficient of L sub k is I, then what is the coefficient of L sub k plus 1? Well, notice that everything in L sub k we bring down to L sub k plus 1. So we already know that there will be an I here. But we have to add the extra terms. And the extra terms are made by adding one from the left and one from the right. In particular, every single term in L sub k is added once to a number on the left and once to a number on the right, which means that every single number on L sub k is added twice, except for the endpoints, which are a and b. B we don't really care about because we're just considering the coefficients of a, but a we do care about, since if we add the coefficients of L sub k twice, and one for adding to the left, one for adding to the right, then we have overcounted this by one time. So we have to subtract 1. So this gives 3i minus 1. And this formula thankfully checks out, because if we plug in I equals 1, then we get 3i minus 1 is equal to 2, which works. And if we plug in 2, we get 5, which works. So now we continue the pattern. If we plug in 5, we get 14. If we plug in 14, we get 41. If we plug in 41, we get 122. And if we plug in 122, we'll get 365. And this is the value corresponding to L6. So this 365 is the coefficient of A. And we also know that this is also the coefficient of B. So the sum of all the terms on row L6 is just 365 times A plus B, which is equal to 365 times 1 over 70 plus 1 over 73, which is equal to, if we go back, this. So D is the answer we want, and we are done.
Hey guys, I'm here back with another math video. Daniel's been gone for MOP, which is a math summer camp you advance to after you pass USAMO or JMO or